The aircraft industry had seen plenty of things that almost worked. What made the helicopter different was something more quietly remarkable. Almost everyone in a position of authority had already decided it never would, and they had done so with considerable technical justification. That dismissal wasn't born from ignorance, it came from engineers who'd calculated the torque, the vibration loads, the power-to-weight margins. It came from military planners who'd built entire doctrines around aircraft that needed runways and delivered speed. And it came, above all, from watching the things actually fly. In the late 1930s, when the first practical helicopters lurched and shook themselves into the air, they did not inspire confidence. They inspired a particular kind of professional concern, the sort that quietly ends programs. This is the story of how a machine that professional aviation called a toy became the one thing war couldn't do without, and of the quiet, stubborn engineer who refused to let the numbers stay bad. Igor Sikorsky had already built one of the largest aircraft in the world by the time most aviators were still learning to land reliably. His four-engined Ilya Muromets, designed in 1913, had flown combat missions over the Eastern Front before the aeroplane had even been trusted to carry more than a single occupant. He understood earlier than most that aviation's real promise lay not in raw speed, but in capability. He had also tried to build a helicopter before. In 1909, as a young man in Kiev, he'd assembled a rotor machine from bamboo and linen. It declined to leave the ground. He set it aside, not because the concept was wrong, but because the engines and materials of the era weren't ready to support it. That patience, long, deliberate, and entirely unsentimental, would prove to be the defining characteristic of everything that followed. By the mid-1930s, Sikorsky had emigrated to the United States, built his company in Connecticut, and produced flying boats that connected continents. He was successful, respected, and by the standards of the industry, comfortable. He returned to the helicopter anyway. There are engineers who pursue what is sensible and engineers who pursue what is possible. Sikorsky had always been the second kind. The problem was never the concept, the problem was the physics, and the physics were, by any honest assessment, genuinely brutal. When a single rotor spins fast enough to generate lift, it simultaneously generates torque, a rotational force that attempts to spin the entire fuselage in the opposite direction. Early designers had understood this for decades. Some proposed counter-rotating rotors, stacked one above the other. Others favored a small vertical tail rotor, mounted at the rear of the fuselage to cancel the twist. But beneath the torque problem lay something more insidious, a fundamental asymmetry that had defeated every serious attempt to build a controllable rotary wing aircraft. As a rotor blade sweeps forward through the air, it moves faster relative to the oncoming flow and generates more lift. As that same blade retreats, it generates markedly less. In a fixed-wing aircraft, this asymmetry is a minor engineering consideration. In a helicopter, it creates a constant rolling moment, an unrelenting tendency to tip the machine onto its side every revolution, at every airspeed. Think of it as trying to balance a spinning plate that insists on tilting in the same direction, permanently, without pause. The solution was flapping hinges, small pivot points that allowed each blade to rise and fall independently, bleeding off asymmetric forces before they could accumulate into something catastrophic, which meant that even a workable solution demanded precision engineering of a kind that most facilities of the era simply couldn't sustain across an entire operational airframe. His VS-300 prototype, a skeletal, open-framed machine that looked considerably more like an industrial experiment than an aircraft, made its first tethered hover in September 1939. The tethering was, under the circumstances, a sensible precaution. What followed over the next 2 years was not triumph. It was a methodical catalogue of instructive failures. The tail rotor configuration was redesigned multiple times. Linkages were rebuilt. The rotor hub was strengthened, adjusted, and strengthened again. There were variants of the VS-300 that couldn't maintain a stable hover without oscillating violently enough to loosen fasteners. There were variants that flew forward adequately but lost hover capability entirely. Each failure narrowed the problem, none of them resolved it quickly. Sikorsky flew many of these iterations himself, a decision that communicated something about either his confidence in the machine or his willingness to serve as its primary test subject, possibly both. The records do not suggest he expressed particular alarm about this arrangement. By 1941, the VS-300 had become the world's most capable practical helicopter. That claim requires immediate context, because most capable practical helicopter in 1941 described a machine that vibrated considerably, demanded intense pilot concentration, and could lift perhaps one passenger alongside its pilot at modest altitude. The Army formally classified it as experimental. This was by most accounts a charitable description. The United States Army Air Forces had observed the development with the kind of careful attention that leads to politely inconclusive procurement correspondence. Their assessment, when it came, was clear. The helicopter was interesting, but not militarily useful. Too slow for reconnaissance near any opponent with anti-aircraft capability. Too vulnerable for operations within range of ground fire. Inadequate payload. And it required a level of pilot skill that couldn't be produced at wartime scale across a training program built for numbers. The doctrine of air power, constructed around range, speed, bomb tonnage, and the proven synergy of fighter and bomber, had no natural space for a vehicle that cruised at roughly 160 km per hour and struggled to reach 1,200 meters. The planners weren't wrong about what the helicopter couldn't do. They were building their analysis on a catalogue of missions that already had dedicated aircraft. The mission that didn't yet have a name, the one where there was no road, no route, and no margin for a second attempt, wasn't written into doctrine yet, because no one had needed to write it. If you think that skepticism was reasonable or inexcusable, leave a comment. The argument still runs among aviation historians. The first serious crack in institutional doubt came not in combat, but in a rescue. In January 1944, a merchant vessel ran into serious difficulty off the Connecticut coast in conditions that made fixed-wing operations effectively impossible. A Sikorsky R-4, the first helicopter to enter limited military production, built directly from the engineering lineage of the VS-300, was dispatched. It hovered over the stricken vessel, deployed a rescue line, and recovered survivors from a position no other aircraft could have occupied. It was not a dramatic military operation, it was a practical one. And in aviation, as in most fields where outcomes matter more than impressions, practical is the more durable kind of impressive. The helicopter hadn't read the doctrine. The R-4 had already been deployed in small numbers to the China-Burma-India theater. The terrain, dense jungle, broken mountain ridges, rivers that erased roads in the monsoon season, made conventional casualty evacuation into a logistical problem measured in days. A small number of wounded soldiers had been extracted from jungle clearings that no fixed-wing aircraft could approach at low speed. The machines were fragile. The pilots were improvising inside flight envelopes the manuals hadn't anticipated. The soldiers were alive. Several of them would not have been by any calculation, and that arithmetic, simple, irreducible, impossible to argue with, was the argument no procurement committee could ultimately rebut. Sikorsky had understood this before the war made it legible to institutions. His engineering notebooks from the early 1940s, dense with control system revisions and rotor blade geometry calculations, are not the notebooks of a man trying to beat a fixed-wing aeroplane at its own game. They are the notebooks of a man constructing something that a trained pilot could actually trust in conditions the manufacturer couldn't predict. The distinction matters more than it first appears. The mainstream narrative frames the helicopter's development as a breakthrough, a burst of invention, a moment when genius resolved what stubbornness had obscured. The records suggest something more patient and less cinematic. Sikorsky didn't invent the concept. The idea of vertical flight had been seriously attempted for decades before him. What he did was make the machine stop being dangerous. He solved the vibration modes that fatigued metal to failure over hours of operation. He refined the control system until a pilot's workload became manageable rather than overwhelming. He removed one specific problem at a time, the ways the helicopter could kill the person flying it. Aviation history has a preference for singular moments: the first flight, the sound barrier, the moon landing. The helicopter's story doesn't offer one of those. It offers something less photogenic and considerably more applicable: the slow, grinding accumulation of correctness. That doesn't look well on a monument. It is nonetheless the accurate account. By the end of the Second World War, the helicopter had a foothold. Production numbers remained in the low hundreds, and tactical doctrine was still forming around a capability that military thinking had not initially wanted. But the foothold was real. It had been purchased in the currency that military institutions ultimately respect above all others: demonstrated irreplaceability. Korea changed the scale. Between 1950 and 1953, military helicopters flew tens of thousands of medical evacuation missions. Field medical data from the period indicated that a wounded soldier who received surgical intervention within roughly an hour of being injured had survival odds that were qualitatively different from those reaching care after several hours by any other means. The helicopter didn't create that medical window. It made the window accessible in terrain where nothing else could operate. The survival rate among casualties who reached forward surgical units improved substantially, not because surgery had advanced between wars, but because elapsed time had been compressed from hours to minutes. MEDEVAC became the operational template for a new understanding of battlefield medicine, and eventually for civilian emergency services, offshore energy operations, and disaster relief across the world. The irony Sikorsky lived to observe was not small. The military had eventually constructed a full doctrine around the helicopter, and that doctrine had been built almost entirely from the characteristics originally cited as disqualifying: too slow, which meant it flew low, below radar, without announcing itself at a distance; no runway dependency, which meant ship decks, mountain clearings, and rooftops in city centers; limited payload, which meant it carried exactly what was critical: one wounded soldier, one rescue swimmer, one component to a location nothing else could reach. The machine hadn't changed its fundamental nature. The understanding of what that nature was genuinely useful for had simply, at considerable cost and over considerable time, caught up with what Sikorsky had been building towards since 1939. One detail tends to be eclipsed by the larger story. The tail rotor configuration that Sikorsky settled on for the R-4, a single main rotor with a small anti-torque tail rotor, has remained the dominant helicopter architecture in the world through every decade of subsequent development. Not because engineering analysis proves it theoretically optimal. Designers will readily acknowledge that coaxial configurations, tandem rotors, and intermeshing blade arrangements each carry specific performance advantages. The Sikorsky layout persisted because it was the layout Sikorsky had actually made reliable. Every subsequent decade has produced serious alternatives. Every subsequent decade, the Sikorsky layout has persisted. Reliability in aviation is not one criterion among several. It is the criterion. Everything else is debated around it. He made the machine trustworthy, And trust, once established in something that people depend on with their lives, has a way of becoming permanent faster than anyone expects. Everything that followed was consequence. Igor Sikorsky died in October 1972, having lived long enough to watch the helicopter become unremarkable. Medical transport aircraft on the rooftops of hospitals in every major city, supply and crew platforms for offshore energy installations, the reliable presence in search and rescue operations conducted in sea states that ground every other form of aviation. He had made the machine trustworthy, and trust colonizes every space that genuinely needs it. He was not, from any account, a man who required the recognition to arrive promptly. It was enough that the work was done. They called it a toy, then they called it impractical, then they called it indispensable, now they barely call it anything at all. It simply exists as infrastructure does, noticed only in its absence. The things that genuinely work stop being inventions and start being furniture. If the real engineering behind the headline is what keeps you here, subscribe. There is considerably more of it, and most of it is stranger than the official record admits.